So we often operate plug flow reactors or packed bed reactors non-adiabatically. In other words, we need a utility to heat or to cool the fluid as it passes through my reactor tubes. And often, if I have heat exchange, because I want lots of area, this is employed by having a tubular reactor where my packed bed, my catalyst or my fluid is not contained in one big tube but in many smaller tubes. This also ensures that I don't have any radial, if I now consider this view from that side, that the temperature is homogeneous throughout the diameter of my reactor. So temperature here at the edges is the same as the temperature at the center of my reactor, which is very difficult to achieve if I have a reactor with a 2-meter diameter compared to lots of small tubes where I have a lot of heat transfer area available and good heat transfer contact between my utility, whether it's a cold utility, so that's the fluid you use to heat up or cool down your reacting mixture. So for the adiabatic case, we proved that I could actually use my linearly shaped energy balance. That is, as long as you start from inlet conditions, you can apply a kind of black box approach up till any point in the reactor and calculate that temperature there, as long as you know the conversion, how each shape look along the length or the volume or the mass of your reactor. Because I have a temperature profile along the length of my reactor, illustrated here is an endothermic reaction where I do apply, in fact, some heating from a constant temperature heating medium. So it wants to cool down, but then it's going to heat up. But the result of this temperature profile along the length of my reactor is that the driving force for heat transfer, which is directly proportional to the temperature difference between the contents at that point in my reactor, therefore at any position, and the temperature of my utility on the inside. It means that the rate at which heat transfer can occur needs me to know exactly how that temperature is going to change inside my reactor as a function of my independent variable. So if I consider the other variables that will be responsible for that rate of heat transfer, it will also be a function of how the utility's temperature change along the volume or whatever independent variable in my reactor. So I may start with a warm utility, but it's going to cool down because of heat transfer along the length of my reactor. Other variables, of course, is the amount of heat transfer area that is available as I've got this incremental slice that I'm now going to evaluate. So I will have its contents at temperature of the reactor, and on the outside I'm going to have the utility with which it exchanges heat, and I need heat transfer area, and I need to know this heat transfer coefficient, the overall heat transfer coefficient that affects the rate at which heat transfer can occur. In many of the examples, we are going to assume a constant utility temperature, and in many of the tutorial problems, and only consider the change in temperature and its effect on heat transfer of the reacting fluid as it moves through my reactor. A constant temperature utility examples is like steam that is just being condensed, so you just use the latent heat, or water that you're evaporating, once again just the latent heat, or once again a fluid for which you have a very huge flow rate, a very large flow rate of my utility, so that if I consider the MCP/dT term, this is so big that the change in temperature along the length pretty much goes to zero. However, for plug flow or packed bed reactors, you will be required to consider the energy balance of the utility, and it's a very easy energy balance because there are no chemical reactions taking place, and be able to describe its shape as a function of the independent variable. So what we do need is we need a differential equation that describes the change in temperature of my reacting fluid as it moves along the independent variable in my reactor. And we also need an equation that describes the rate of change of my utility as it moves from the inlet from the perspective of my reactants, of course, along the length of my reactor. Because heat transfer area is such a crucial rate determining parameter where heat transfer is concerned, these non-adiabatic plug flow or packed bed reactors are constructed as tubular reactors, so it looks like a shell and tube heat exchanger. So you will have your tube bundle through which your reactants will flow, in which you are going to pack your catalyst particles, and then you've got your shell side with your cooling and your heating medium. And many of the design principles are really similar to those where heat transfer is concerned that you studied for shell and tube heat exchangers in CIO. So what's shown on this slide over here is the procedure to do an energy balance over a small slice of volume of my reactor. So we choose volume as our independent variable in this derivation, and we see what happens in a very small slice of my reactor. As fluid flows into it at a temperature at the inlet, and the temperature is changed for several reasons, because there is an exo or an endothermic reaction, because of the sensible heat of my components, and now also because heat transfer can take place between my flowing streams and a utility. So now, of course, I not only have the change in enthalpy over that small volume that I'm going to take the limit of as it goes to 0, I also have heat transfer that can occur in that small volume. And that heat transfer there is equal to the overall heat transfer coefficient, the driving force for heat transfer, which is the difference between my utility temperature and the temperature of my fluid in that small little slice, as well as the small incremental area for heat transfer that I have available. So of course now that area for heat transfer is not the cross-sectional area of my tube, but it just involves the circumference. So that is where heat transfer will take place, and that's why I use the circumference multiplied by that small length, because that will give me the total area that's available in that slice for heat transfer. And what's happening here in this equation is that I now substitute the volume of that small slice, so that I can calculate a parameter that gives me the surface area available for heat transfer per bed volume in cubic meters. So this will be something that is at units of per meter, but what I need to take into consideration is that it's an area divided by the total volume of that slice. And this is where I use volume as my independent variable. So it says as you move along that length of the reactor for each small little dV, this is the area that you will have available. So area has got units, this small a has got units of per meter for a tubular reactor, which is always the reactor types, and I don't know of any other kind of reactor type that we are going to consider. It will always result in an equation that it says it's inversely proportional to the diameter of my tube. So the smaller I make the tube diameter, the larger I make the area that is available for heat transfer per cubic meter of my reactor as the fluid flows through my reactor. And because I don't have a reactor that looks like this, that parameter, which is the area available per cubic meter bed, will remain constant along the length of the reactor. The only important thing to consider is how do I change that if I want what is the heat transfer area available per catalyst mass, if I want to change my independent variable to mass, or if I want to change my independent variable to length. And that is for the class discussion, but please see if you can make the units work in order to figure out what is missing in order for you to change this to a per kilogram catalyst or to a per meter catalyst value. So just the application remaining for our single reaction. We once again want the differential equation that describes the change in temperature along the volume of my reactor as a function of my other variables, which will be maybe the utility temperature as well as the extent of my reaction that we can for a single reaction write in terms of X. And so just I've rearranged over here, and remember dE we can substitute with our dFA over the stoichiometric number, and in this case the stoichiometric number is -1. So the two negatives will cancel each other out, and that is why I end up with this term plus that rate of A multiplied by the heat of reaction divided by the sum of everything flowing through that reactor. At that point, of course, I forgot it over there. My simplifying assumption is if the del Cp of the reaction is equal to 0, that del H reaction, I don't need an extra algebraic equation to calculate for that in my function. I may need an equation to calculate for the utility temperature. So if it's a constant, it's a parameter that is defined outside of the function where I define my differential, return my differential equations. But if not, I need an extra differential equation that describes how the utility changes along the volume of the reactor. So finally, for a gas phase reaction, in a packed bed reactor, where I will now have to consider frictional pressure losses, let's just look at the differential equations that we will need to solve in order to design or evaluate a specific reactor. So of course I have a differential equation for each of my molar flow rates, and these will be functions of my rates. Then I will have my energy balance, and I will have my Ergen equation to describe the pressure drop. If I now go into my equations, once I've now written them down, look at, do I need parameters, define them outside or calculate them outside of my function. UA, I will calculate the heat transfer, overall heat transfer coefficient. What is the A value? Remember the A value directly related to inverse of the diameter of my tubes. Concentrations I can calculate, but Q will vary because it's a gas phase reactor, and it's going to vary according to the ideal gas law. So once again, a word of warning, if you want to write Q as a differential equation, please note that this is a variable, temperature is a variable, and pressure is a variable. So you have to apply your product rule and your quotient rule, and you really need to pay attention to the maths if you do that. For those who enjoy it, it is a doable exercise. I, however, prefer to use this algebraic equation. I'm less likely to make silly mistakes. And what I mean when I say use ratios, it's safer with mixed units, is if I have if this is in moles per second and this is in kilopascals, instead of having to remember that I need to convert and then calculate the flow rate, I just calculate my inlet volumetric flow rate in the units I desire, and then I can calculate Q at any point just by having Q naught multiplied by this whole lot of terms over there, and I've got a lower risk of making errors in my units, but that is of course up to you.